Shall we start, ma'am?
Yes, we can start.
Yes. Okay. Welcome to 147th episode of Creative Online Weekend Talks. Today we are more excited to uh, uh, it- uh, take into the fascinating world of X-ray astronomy. Creative. We are a community driven by a passion for knowledge, guiding by our motto, Knowledge Square. We believe that sharing knowledge enriches us all, focusing constructive thinking across various domains. Our mission is to explore the unreachable horizon, bringing new insight to eager minds. In this episode, we delve into X-ray astronomy, a field that reveals the hidden high-energy universe from the explosive of supernova to the powerful emission of black hole. X-ray astronomy allows us to see phenomena invisible to ordinary telescope. Join us as we uncover the secret of cosmos through X-ray observation and tune into our YouTube channel Creative GBD for the live stream for this enlightening discussion. To present this episode, we have Dr. MC Ramadevi ma'am with us today. To introduce today's speaker, I call Ganesh, creative volunteer, to introduce today's speaker. Over to Ganesh.
Yes, ma'am. Hi, good afternoon, everyone. I'm Ganeshal. It's a great pleasure to welcome our guest of honor today. On the behalf of Creative Team, I welcome our chief guest, Dr. MC Ramadevi, scientist, UR Satellite Center, Space Astronomy Group. She joined ISRO in 2003, initially as a research fellow, and then she did PhD and joined as scientist in 2007. She have expertise in design, development testing, and calibration of X-ray detectors for space-based instruments. Principal investigator of one of the payloads on Astrosat, the Scanning Sky Monitor, which is an X-ray instrument to scan the sky for X-ray transients and detect and locate the sources and also carry out long-term monitoring of the sources. Research interests are X-ray instrumentation and X-ray astronomy, X-ray transients, black hole binaries, etc. Presently part of Expect instrument onboard Exposat and also Solexis onboard Aditya L1. Part of a calibration team of both instruments and also science working groups. She have initiated few technology development programs for new X-ray instruments to be flown in future missions. She even have several research publications with research carried out till now. Thank you for giving an opportunity to welcome our guest.
Thank you, Ganesh. Welcoming one and all for today's session and hand overing to Rama ma'am. Over to you, ma'am. 1 minute, I'll make you. Okay. Shall I start sharing, ma'am?
I'm muted. Yeah, yes. Yeah, please.
Okay.
Go ahead. Thank you. Yeah.
Is it visible, ma'am?
Yeah, it's visible.
Slide mode.
Yes.
Yes.
It's visible, yeah. So, shall we go ahead? Okay. So, I assume the audience is largely kids of school kids. So, I made my presentation to a very basic level, and I would try to make it very interesting as much as possible. Yeah. And it can be interactive too. Can we have it interactive or just go ahead in a smooth way? How should I carry it forward?
Ma'am, you finish your presentation. Later we take questions, ma'am.
Oh, okay, fine. Okay, so I was thinking if it were kids, interactions would have been nice. Yeah, fine. I will keep to the presentation.
Yes.
So today's talk is on X-ray astronomy. Okay, so before going to astronomy, I need to clarify or give a insight on what X-rays are. Okay, so we all would have heard of light, meaning we are very familiar with light. So all what we see around us is because it's all the presence of radiation or light. Okay, so we are very familiar with sunlight, the tube light, torch light, the light from a mobile, light from the TV, etc., everything. So all what our eyes are able to see is largely from that very small spectrum, very small band of the electromagnetic spectrum, which is a visible spectrum. Okay, so visible, when I say, everyone would be knowing what VIBGYOR is. VIBGYOR is like violet, indigo, blue, red, orange, green, and red. VIBGYOR, yeah, green, yellow, orange, and red. Okay, so these all are the colors which we define as per the wavelength. You must be familiar with wavelength, I assume. Wavelength is basically the energy associated with the light what we are seeing. Okay, the quantum of radiation what we are seeing. So largely our eyes is familiar to only the visible spectrum, which is a very narrow band in the complete electromagnetic spectrum. So for the kids who are familiar with just light, it is a very, very small band. You know, I am, somebody else is sharing, so I cannot use a pointer also. So you see the bulb there, the bulb and the sun drawn. So the bulb is a very, colorful things shown there. That is a very narrow band, visible spectrum, which our eyes are capable of seeing. Okay, but the electromagnetic spectrum, basically the radiation or the light, is a very large band which has many different wavelengths. Okay, so it is, if you see on the top, what is shown is like radio, microwaves, infrared, then a bulb showing the visible, then ultraviolet, x-rays, and gamma rays. So this picture is borrowed from the internet. So to give a very good pictorial representation of what wavelength are we seeing. Okay, so radio waves means what, as the name suggests, the frequencies which are used in to telecast news via radios, etc., we actually use that frequency is nothing but wavelength, another form of wavelength or energy of the radiation. So radio waves is in that very long wavelength. Then the microwaves, the microwave, actually the microwave which you use in your houses, the wavelength used there is actually the microwave wavelength band. Then infrared is like the heat. What we feel comes in the infrared. And the visible is the optical wave band which we actually see. Then the ultraviolet is little on the higher energy side, and X-rays come after that. So X-rays and gamma rays are very, very energetic form of radiation. And where do we use X-rays? Basically, when you go to hospitals to do an X-ray of your, if you have a fracture, if your arm is paining, and you want to know what is inside, is the bone broken? So you do an X-ray. That wave band which the radiation comes in is called the X-ray wave band, and beyond that is the gamma rays. Okay, so this is the electromagnetic spectrum. So if this slide has stuck in your brain, to understand what electromagnetic spectrum is, we are going to discuss only part of X-rays, and that to associate with astronomical observations. Okay, go to the next slide, please. So now X-rays, when we say, you need to know how these X-rays are produced. Okay, X-rays were discovered in the 18th century. 1895. One scientist called professor called Wilhelm Röntgen, in his lab has discovered this X-ray. So he didn't know when he saw this radiation, when he was experimenting with things, when he saw this effect of the radiation which he in his films, when he saw, he didn't know what this effect was, and he realized that something is coming to form this thing in the film what he was having, and he named it X-ray. So later, in the many years which we have come across with advancement in sciences, we realize that X-rays are produced by different methods. Okay, uh, you know, for very preliminary school kids, this would be too much, but just take the name. X-rays are produced by four different methods or four different phenomena. Okay, the photoelectric effect, which is written here as fluorescence, basically the photoelectric is atomic emission. Okay, there are something called atomic emission and nuclear emission. Okay, so nuclear emission meaning some radiation emitted from the nucleus of the atom. If you're familiar with the atom has a nucleus and electrons revolving around it. So any emission come from the nucleus, we call it nuclear emission, which goes in very high energies. That comes under gamma rays. Okay, and anything coming in the electron shells, the atom has electrons revolving around the nucleus. So anything coming from the emission from the nuclear, energy levels in the atomic energy levels in the periphery of the nucleus, wherein you have the electrons revolving around the nucleus, that emission is largely in X-rays. And we have this photoelectric effect, then the Bremsstrahlung, the synchrotron, and inverse Compton. All these are limited to atomic level emission, wherein the atom in an excited state, when it de-excites, gives rise to an X-rays. And Bremsstrahlung is nothing but an electron or an ionized atom. Ionized atom means what? One electron is removed, an ionized atom. When in the presence of another ion, electron in the presence of an ion, will give rise to Bremsstrahlung, which again is an X-ray. So the electron accelerates in the presence of photon and gives rise to X-rays. That is one X-ray protection. Then an electron, when in a magnetic field, when an electron gyrates in a magnetic field, it's accelerated, and that energy gained by the electron is given in the form of radiation. That's again X-rays. And then inverse Compton, you would have heard of Compton scattering, meaning a photon hitting a electron, and then the electron's energy is gained by the photon, and you get the energy of the photons in form of X-rays. High meaning basically it absorbs energy from the electron and gives X-rays. So these are different methods by which X-rays are produced, and that is what you observe as radiation in the X-ray wave band. Go to the next slide, please. Okay, so now coming to astronomy. So just from the two slides, we have learned what electromagnetic spectrum is and what part of the electromagnetic spectrum is the X-rays. X-rays are very high energetic radiation. Okay, and then how X-rays are produced in meaning how is it basically understood? It's basically atomic level emission. You can remember this. Okay, now coming to astronomy. So what do we all know about astronomy? Astronomy is, understanding universe. That's the simplest terms. So what is the universe? Universe is like, we are just on Earth, which is a very small speck in the universe. Okay, universe is very vast, and there are stars, there are galaxies, there are planets, there are asteroids, there are meteors, so many things. There are many things. These are the terms which I tell. The terms like stars, galaxies, planets are known to a very small kid. But as you grow, you realize there is a lot more to explore in the universe, a lot more. Many of you would have heard of black holes, many of you would have heard of neutron stars, which are very exotic objects. The manifestation of emission mechanisms which happen in these different class of objects is what we observe as the universe today. We just observe, we just get the radiation from all these class of objects. We sit on Earth, we observe them, and we make stories to understand the universe. Okay, have you ever gazed in the night sky? The depth of the sky is really stunning. You go away from the city and just observe the sky. The sky has stars, and it's black background with just specks of light. All what we have to see from Earth, what we could see from Earth. And now the understanding of the universe is immense. How is this happening? It's all we study the data, we formulate theories, we relate it to the observations, and that's how we understand this is what is there in the universe around us. Okay, so here is an example, like Pleiades cluster. It's like seven sisters, they call it, and people would have been more familiar if I had put the Big Dipper. It's like a big parallelogram. People, the ancient astronomers tried to make patterns in the sky. So you just imagine you are a naive kid, a human being sitting on surface of the earth, just looking at the sky, and what do we see? You just see the light, arrangement of the light, a pattern of the light. Have you ever gazed? You should go tonight to your terrace or anywhere out and just observe the sky to see what are all the things I see in the sky. You will see the moon, definitely, it's a big object, and you see away from the moon you will see different stars. And if you observe the sky every other day, you will definitely see patterns in the sky. It's very interesting to map the patterns, and you see the patterns moving. The moon moves from east to west. The sun rises in the east and sets in the west. So it keeps moving. Similarly, stars also, if you keep seeing from the earth, you will see them to be moving, but it's in a relative motion, which makes us feel that it's moving. It's not actually moving because the earth is rotating. We see them moving. Okay, so it all started astronomy. It all started with the man observing the sky. Next slide, please. So how did we observe? Initially the picture here, the left side, what is shown here, it's all drawings, handmade drawings by very old astronomers, or you don't call them astronomers, human who is curious, a man who is curious starts to sketch what he observes in the sky. Like I said, the patterns keep moving. You just sketch in the pen in your rough notebook today, and tomorrow you can say, hey, I saw this point, this bright point in that location. But you can't just make points, you have to make patterns. Then you will say, like, oh, the big dipper pattern, which was a parallelogram or a rectangle, today I'm seeing it shifted somewhere. What is happening? Or what time of the day am I seeing this? Is this, did I see yesterday at 7 o'clock, today at 8 o'clock? This is the way they mapped it. And they found every other day they map it. And every other day, there are, if you see the stars, they go as a group, but there can be something which is moving faster. If you observe the sky, it may be faster as compared to the background of the star constellation, which is not moving at all. So this faster thing, you may see a satellite, our own satellite, or any other NASA's or ESA's satellite moving in the sky faster. And you realize it's satellite because you there are maps to figure out satellites too. And then they may be faster than planets, but planets are faster than stars. So the movement of these are mapped on chart papers or notebooks, and then they realize, they postulated theories. All what you are doing is you're sitting on earth and you're seeing outside. That's all. And you need to understand. So you make patterns, you make sketches, then you postulate theories, and then you verify. Okay, so very olden days, 16th century or even BC, those times man was curious, and then over years it has been understood that we are on a planet which is moving around the sun, which is, the sun forms a solar system with many planets around it. So just from the drawings, many theories came up. Initially they thought sun is moving around earth. That's natural, no? You're sitting on earth and sun is moving around you, so you can postulate a theory, hey, I am sitting on earth and I see the sun moving, so the sun is revolving around earth. That was the theory which was postulated first. And with much rigor and study of the planetary motions, it was understood that no, it's not the sun, it's the sun is sitting at the center and earth is revolving, and that's why it appears like the sun is moving around earth. And like earth, every other planet is revolving around the sun. This is how it was done, and it was all done in the optical waveband, in the very narrow visible waveband, and with eyes, naked eyes. Okay, then the curiosity is even more, and people wanted to know with higher resolution. I need to collect more. I need to see. Have you seen planets with through a telescope? If you see the night sky, you will see it as Mars as just a small speck, a red star. Okay, and the Jupiter will be very bright bluish. Venus is more bluish. So it is a bright star in the sky, but it slightly does not twinkle as compared to the other stars. This is another phenomena which was studied over time. Planets don't twinkle because they are closer as compared to far off stars. And so this Jupiter will simply look like a bright object in the sky. But when you see it through a telescope, amazing! You see the the ring around Jupiter. Sorry, that is Saturn. Jupiter has different layers of visible spots and other things, and Saturn is, again, you see the rings around it in an inclined manner. These things, when you observe with a telescope, it's amazing. So with telescopes came more further studies. Okay, go to the next slide, please. Hello. Yeah, so telescopes, what they do, light, I have just given a figure of like light from distant stars are coming. There were two types of telescopes. One is refracting telescope and a reflecting telescope. Okay, now after many initial years of using both these telescopes, people realize that the second one is very effective in observing. So we have refracting telescope and reflecting telescope. So refraction, when I say, you would have heard of lens. The glass, the specs what you have, they all have lens. they all act as refracting optics. Okay, it actually converges the light to you. So that is what is on the top. And the second one is reflecting. Again, the light from this is focused on the mirror, which is A, and then it is reflected back to mirror B. And then we have the focal point where we put the detectors, the instruments, the detectors. So instead of our eyes, the focal point can have our eyes also. The previous slide one end is the object end, the other end is the eyes. Yeah, other end is the eyes, which is a very good detector in the visible wave band. As I told you, violet to red, violet, indigo blue, yellow, green, orange, red, everything our eyes can detect all these wavelengths. So that's an optical waveband. So you put your eyes, you see only the optical waveband. Okay. Now, going further, next slide, please. Going further, what they did, they replaced the eyes with a instrument. Eyes can only see. Okay, it'll see and it'll forget. But if you want a record of it, what do? You want a record of what I observed. You want to show people what it is. The camera, what you use? The camera in your mobiles, the separate cameras if you have held. Kids may not know about this until unless you have a passion for photography, you won't buy a camera. So, olden days, cameras were only there to record images. Nowadays, mobiles are there. Turn over whichever place you want to click, 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 click. You get pictures. Okay. So that instead of the eyes, you put a camera, a charge coupled device, a camera. You record the images in that. Okay. So what do you see? If I see the Saturn through telescope and I come and tell my friends like, hey, I saw a nice ring around it. Wow, so beautiful. He won't believe until unless he will be taken there to see it. So what would you do? You put a camera, you click that, you record it, and then come and say, hey, I have a proof. Look at this. So olden days, these telescopes were the ones which were doing the optical observations, and lot further studies were taken up. What further studies? Go to the next slide, please. Yeah, so birth of astrophysics, physics. Astronomy is generally like, this is what I observe, this is what I postulate, this is what we believe. That's the way it was. But you bring in the physics. What is physics? Physics is like a more defined process of meaning, a more defined way of looking at things. So I looked at the sun. Say you look at the sun with a telescope. This plot here, the different colors there, you see dark lines in between, very dark lines. Some places you see dark lines, some places you don't see dark line. It's an amazing phenomena. The physics, what I said, the second slide of mine, which showed X-ray emission, X-ray production. A similar process, say if the atomic lines are well defined, the energy levels, the quantum of radiation is very much defined with the atoms. So if I have any dark lines, this plot here, what you're seeing is called a spectra. What it means by spectra is basically, take it like this. I have this much intensity in the red and different intensity in yellow, different intensity in violet. That way, when you distinguish intensity or brightness as a function of color, as a function of wavelength, you call that a spectra. Okay. So this figure here is actually a spectra of the sun. Okay, in the optical. So some dark lines there. Somebody saw, like, Fraunhofer was a scientist long back. When he looked at the spectra, like, something is different. It's not uniform throughout. Oh, I find two dark lines. There are few places you see dark lines. Then what he said, this must be something which is absorbed by the atoms in the photosphere of the sun. What it means by photosphere is the outermost layer of the sun. All of you know that radiation from the sun is basically coming because there's nuclear fusion happening at the core of the sun, and it emits radiation. Okay, so when it comes out, we with our eyes are able to see it in an optical waveband. Now when you put a spectrometer or an instrument to observe that same band, you will see it differently. You see some things are missing, some wavelengths you see, it is absorbed, the intensity is zero, it's black, there's no emission. Then they related that particular wavelength, that particular lambda, to find out what is actually absorbing. So I'm throwing something at you, and in between you put some barricade, okay? So say the barricade stops it; it does not pass through. So this is like some atoms there can absorb certain wavelengths, and you don't see them. So it's absorption spectroscopy. And the beauty of this is you will be able to identify the atom. All what you're doing is you are having the spectrum. You're sitting on Earth. Radiation is coming far from very far of distance from the sun. You are having some instrument on your table or on your laboratory or on your observatory. You call it observatory. The telescopes are put in separate places called observatories. Okay, so you observe with the telescope which I showed in the previous slide, and you all what you get is something like this. And what is it? You analyze the data. You look at the data and you say like, oh, something interesting is there. So how do I relate this to? At this particular wavelength, I don't see any light. At other wavelengths, I see the light. That means something is there to absorb that wavelength. And what is it? That energy of that particular absorption line will link to what atom is present in the surface of the sun. You got an understanding just by analyzing the radiation what you observe with your instrument. You are able to say what is there in the surface of the sun. Isn't that interesting? So this is the way that people started to observe. Now you have a very, very magnifying telescope, very highly sensitive telescope which can observe the sun. Now I have other stars in the sky, isn't it? And all of you know that like sun, there are many other stars in the sky, and stars of different classifications. How this was done? People started observing different stars. Okay, not just look at the sun. The sun is, we don't see stars in the bright light in the daylight, because sun is the brightest star. It's very bright that it outshines the nearby stars. There are many stars still in the night, in the day sky. Along with the sun, you still have stars in the sky, but you're not seeing it because sun is very bright. Give an example, like I have a very bright torchlight, or simply in a night, you're driving in the night and you see something very bright coming. You won't be able to see anything else, only the light. That's what is happening in the daytime. You're seeing only the sun. There are still stars around. Okay, then people started to realize that, oh, I need to understand what is happening in the stars also. Then let me observe it in the night time. With the same instrument, I observe the stars in the night time. So go to the next slide, please. So what they found, every other star starts to show similar energy spectra. They look similar, correct? Like how sun is showing this kind of a profile, other stars also started to show. Then they found difference in different types of spectra. Here what is shown is like, the sun's energy. I told you spectra. So spectra is nothing but wavelength versus intensity. If you can take this as a point, wavelength versus intensity. So the sun spectra is a black body spectrum. We call it a black body spectrum. This is a new term probably for many of you, which you will learn in your higher classes. So uniqueness of the black body spectrum is like, for a given temperature, one temperature, the black body is like thermalized system wherein the emission and absorption are thermalized, and you have it associated with just one temperature. So if you were to plot a black body, it would look like this. Different temperatures are written: 6000 Kelvin, 5000 Kelvin. Those for different temperatures, the black body spectrum is unique. So sun spectrum is a black body spectrum with a temperature of about 5590 I think 5590. That surface temperature of the sun comes around 5590 Kelvin. Okay, then what you have is, down below there is continuous spectrum, emission spectrum, absorption spectrum. Like how I explained in the previous slide, with just studying the spectra, you will be able to tell what are all the atomic elements present in the star which you're observing. So according to that, the stars were classified. Okay, why I'm going into all these details is like, astronomy, how it started, and meaning how people started to make sense out of what they observe, and then how it went further and further to understand many more things in the other wavebands like X-rays. Okay, so classification of stars were done purely with the optical observations. Go to the next slide, please. And I can quickly brush through many things. So few ground based optical observatories. So since you know that I have a telescope, I can make wonders with the data what I get. I can postulate theories, I can study different class of objects. These are not just stars, there are many other types of objects in the sky. So these are few examples of optical ground based. When I say ground based, we have it on Earth. Ground based telescopes and optical waveband. So this IAO Hanley is closer to the Himalayan foothills. So it's like Indian Astronomy Observatory, and it has been managed by IIA in Bangalore, Indian Institute of Astrophysics in Bangalore. Then VBO Vainababu Observatory in Kavalur is also ours. Then there's Kodaikanal. There are a lot more. I've just put few examples here. Kodaikanal Observatory is largely a solar observatory, but it is it's still maintained and it is observed. Observations are carried out. Then this Gemini, Palomar, and Keck are at different places on Earth, different US and other places. But if you are interested to know about more on optical observatories, you can Google it and you get umpteen number of optical observatories there. Go to the next slide, please. Okay, so now in the waveband, this is another example. Radio telescopes, like optical telescopes, we have this radio telescopes also on ground, which means in the radio waveband, the similar sources are observed. You observe the same star in radio, or you observe a galaxy in radio, and you get the data and you make stories and theories and understanding, and that's how we have the present understanding of the universe. Next slide, please. Okay, now we know that with optical observatories, we were able to do great science. We were able to classify the stars. We were able to tell many things. But curiosity further goes in. What if I send a telescope to the space? There's something called atmospheric seeing, meaning the stars twinkle because you have the atmospheric turbulences coming in play, that it does not give a clear picture. So what we do, we thought, okay, to observe it even better, let us send a telescope to the space. We escape the atmosphere and we'll have very good clarity for observation. That is how this Hubble Space Telescope was launched. And you should Google about this Hubble Space Telescope to understand how it works. And, many discoveries have come out of this. Next slide, please. Okay, this, as I told you, if you observe the planets with the telescope on ground, you will be able to see, for example, Saturn, you will be able to see the rings and with good clarity. But these are pictures which are taken by the Hubble Space Telescope in space. So the clarity and the picture of images, whatever obtained in optical by the Hubble Space Telescope, which is in space, is amazing. So now few of the slides I am just showing you pictures for you to kindle your curiosity to go and know about how this have been observed. So this is a montage of the solar system. Next slide, please. Yeah. Now, like how I said, there are, other than stars, you have the planets. Then there's something called nebula. Nebula is nothing but, there are hot gaseous regions in the universe. Meaning, we have the solar system, and then when we go a little more beyond that, we have the interstellar medium. Meaning, between the stars, you have a huge medium. A little go further, you have the galaxy. Then you have many clusters of galaxies. So, but between these regions, you have hot gaseous regions which emit in different wavelengths, and there are structures to it. And how these are produced, these nebular regions are host regions for production of stars. The sun has been in the very billions of years back. How is the sun formed? Is like from such gaseous region. The atoms and molecules are attracted and they fuse together to initiate a process to form the star. Okay, so these are star formation regions, gaseous regions in the interstellar medium, and these are observed by the pictures here shown are observed by Hubble Space Telescope. So, and there are different structures to it. So helix nebula, the cone nebula, the cat's eye nebula, these, the namings are given from the features which are observed. And the same, these nebular regions are again, how are they formed? They are formed from death of stars. When a star dies, it throws out matter into the interstellar medium, and you have such dense regions wherein you have the ionized plasma, which again helps formation of stars. Okay, this is a cycle. Go to the next slide, please. Okay, so as I told you, the supernova remnants. So yeah, the supernova remnants is where the when a star dies, around that core of the star, you have this matter thrown around, which we call the class of objects as supernova remnants. Now, this galaxies are nothing but collection of stars. Many billions of stars together form galaxies. So, like how say you have the sun and planets around it. Similarly, you can have different kinds of solar systems, stellar systems, you call them. Sun system, which is bound to the sun, is called solar. And similar star plus planetary systems are called other stellar systems. There are an umpteen number of stellar systems around. So, like we have one star and billions of stars, these stars together form a galaxy, billions of stars, and the galaxies have different structures and shapes. So, these are again images by the Hubble in optical. And are you not, say you are a person looking at these images, somebody comes and say, hey, I observed this. So every galaxy, there are, every picture shown in this slide is very unique. The one at the left bottom, you have two clear cut arms around it, and then on the top it's just like a bulge. It's a very uniform one. Then on the right it's like a perfect ellipse, and then the right bottom you have clear distinct arms coming out, and not just two, many of them. So these again triggers a curiosity to understand what is actually causing this formation of different kind of structures, and these are all in optical. Go to the next slide, please. Yeah, then comes the globular cluster, like clusters of stars. These are again pictures taken by Hubble. Next. Okay, so there are variety of kinds of objects seen by Hubble just in optical. Now remember the first slide, the electromagnetic spectrum, wherein all these observations are done only in the very narrow visible band, and you get such colorful universe. The knowledge which you have obtained by observing different kinds of objects and the phenomena and the process to produce this, what has gone into the, when you analyze the spectra of these, you realize that there are different kinds of elements present in these systems. And when you try to understand, it's not just the presence of element. The little more you go into the spectroscopy, the study of spectra of any object is called spectroscopy. When you do the spectroscopy, the complete emission, like the black body emission is it's called a continuum. It's not a line, it's a continuum. It's a broad emission happening in a broad band. So when you study that, you realize, or you understand what is the emission mechanism, the process of emission happening in these systems to give rise to such unique images or unique data which you observe in these class of objects. Okay, so like for example, this Saturn, which is in the very left bottom, when I study, if I am doing image based, location based study, if I want to know what is happening, what is the element present in the rings of Saturn, then what I do, I only focus on that ring area, meaning if it is an image, I pick that data of that corner of the ring, and then I study the energy spectra of that to find out what are the elements in that. And if I want to study on the topmost left, it's a nebula. And if I have a continuum, it's a broad emission continuum, then I fit with models, theoretical models, which is already there. The slide has gone in my screen. Is it visible for
1 minute,
others?
ma'am.
Yeah.
1 minute.
Yeah, that's okay. So
You
what I
can.
do is I try to study the complete spectrum by theoretical modeling, meaning I will have a model which is generated via assumptions and theories, and I use that model on the data and see if it fits well, and I try to understand is this the emission, what is happening to give rise to this kind of a energy spectra. So that is how you do for different class of objects, different types of objects. So if you were to take up astronomy as your future career, things what you would do is like learn the energy spectra. Then the other thing is something called a light curve. You know, light curve means okay, going before going to the light curve, like images. You know, if what is an image? What is an image? Image means it's a intensity distribution within what you see, correct? Some things are bright, some things are faint, some things are so it makes a pattern. So you study the pattern, which the study domain is called time, imaging studies of any object. Okay, first is energy spectra, then imaging, then you try to study the intensity variations with time. Means the same nebula what you watch today, after so many hundreds of years there will be some changes in the image. It won't look the same. So what has changed it? Over time the intensity would have changed. That is what is a light curve. So different kinds of objects and different techniques to study these objects is what has helped us evolve in understanding, evolve our understanding about the universe and the present state of understanding what we have about that. Next slide please. So, okay, this is a Hubble deep field. You should read about this. What it means is the thing stares at one part of the sky for a long time, and you find many specks of things. So what you see here is a wide field of Hubble, and many specks, whatever seen there, are all galaxies, different galaxies, clusters of galaxies. So it's not like stars, planets, nebula, everything put together in a galaxy, then many clusters of galaxies together, and billions of galaxies observed. And different way of, you observe it like, flat, thin, bulged, etc. Different angle of observations can also give this kind of a distinct feature. So there are a lot more to learn in this universe with the radiation what we observe. Next slide, please. I was talking about different class of objects, the nebula, the galaxy, how they look, etc. The sun is a very close star to us, very familiar star. So when you look at the sun in the very early morning, you see it like a ball of orange ball, right? And in the evening also you see like that. In the daytime you see it's very bright with, you can't actually look at it. So now this picture here is basically shown in visible and ultraviolet. Ultraviolet is another waveband, visible is another waveband. Visible with certain filters it is shown. You know how different it looks. How different it looks. You say if I don't observe the sun in ultraviolet, I didn't have the image at all, assume. What will I think about the sun? Now, sun is a round spot, that's it. It's there in the sky, yeah, it's just round spot, that's it. How it produces radiation? This nuclear fusion is happening inside and radiation is coming, that's it. But when I looked at the sun with in the UV wave band, yeah, what's happening there? Oh, there are many features on the sun. I didn't see this with my eye, with my naked eye, or with some filter. Please don't look at the sun with naked eye, it's not safe. Morning and evening staring is okay, but the daytime sun, it's like you have very low atmosphere for it. You don't have a column to observe, so please, that would not be a good idea to stare at the sun. Your eyes are not safe. So now in optical it's so boring. Don't call it boring. Even in the optical, the dots there, a curious kid would say like, hey, I see some dots there. What are those dots? What could cause the dots? Okay, those are sunspots. With the understanding of whatever physics we do today, we have known that those are sunspots. Sunspots are linked to magnetic field in the sun. Something happening there. Same thing when I observe in UV. Oh, it's even more dynamic, yeah. And then say this image, what I see in UV, after a while, the features don't look the same. They're very different. If you see a video, I don't have a video here. I wanted to, but lack of time. Sorry, but you should Google to see. Hinode, HINODE is a solar telescope observatory which is observed, and many beautiful videos. You simply say videos of the sun in Google, and you will get umpteen number of videos, and they are all not faked videos. They are actually observations with given some colors to make it more beautiful, but they are actually observed. Okay, so this UV kindles the curiosity more. Oh, what is actually happening in this? Now, next slide, please. Now, look at the sun in X-rays. We are talking about X-rays, right? So X-rays, it's very different. in the UV it had some features and it was limited to some region. In X-rays, it's even more. Sun is half the size of the picture what you're seeing here. So almost double the size of the sun area, I have X-rays coming from the sun. Oh my God, I didn't know this. There are X-rays coming from the sun. So X-rays coming from the sun are reaching you. Are they reaching you? Optical definitely coming down to the earth because you're seeing sunlight. You're getting the sun rays. So X-rays are also there. Oh, X-rays are coming to the earth. If they are X-rays are coming to X-rays, for your information, X-rays are harmful to our skin and body. They are harmful, and still we do X-rays because it's inevitable. You go to do X-rays, but they are in short exposure, very very short exposures, and it is made sure that you are not affected with that. But many number of X-rays are not good for health. Okay, so not good for the human body. So short exposure is okay, but sun is always there. X-rays, it's always emitting X-rays. Quiet sun is also having X-rays, and there are something called solar flares. Suddenly it flares, increased intensity coming from the sun. Okay, it goes very high in intensity, and that affects communication, affects satellites, many things. There is a different topic of research under this which is called space weather. Whatever thrown out from the sun, it throws out energetic radiation, and it throws out matter which is ionized plasma, which can affect telescope, many satellites, observatories there, and many instruments which you fly to the space, and at the same time that reaches the earth also. And we are protected. How? X-rays from the sun don't affect us. How? Go to the next slide, please. Yeah. So we are on the surface of the earth with a huge column of atmosphere. Huge column of atmosphere. So what is Earth's atmosphere? Earth's atmosphere contains different elements. I have only 10 more minutes and I have a lot of slides to talk. Can I overshoot a little bit? Is that okay?
Yes, ma'am.
Yeah. So, okay. So the Earth's atmosphere absorbs the X-rays. Absorbs in the sense it does. It's as I told you, the atoms and molecules, etc., in the atmosphere simply absorbs and does not allow the X-rays come to the surface of the Earth. So here, this plot clearly shows. The on the top is a map, is a scale of electromagnetic spectrum, which shows from radio, and microwave is like 1 meter. Meter is a unit to measure wavelength. Okay, meter or angstrom, whichever you can. So 1 millimeter, then you can convert it. Then you have this visible, which is very small, and you can see the picture shows like the visible comes down to the rocks on the bottom. That is sea level. So if you want to observe the sun in the optical, you can sit on the surface of the earth and observe. But if you were to see the X-rays and gamma rays, the violet purple lines, they are all absorbed till that depth. Whatever coming down, it's absorbed. Then nothing comes to the surface of the earth. So at altitudes, the y-axis is shown in altitudes. Okay, altitude is nothing but it's distance from the surface of the earth. So at around about 100 kilometers from the surface of the earth, till there, at around that, completely all the X-rays are absorbed, so they don't come to the surface of the earth. Next slide, please. So yeah, so this is a pictorial representation. You have a dish like thing on the right side, the 1 meter, that range is a radio. So radiations in the radio waveband come to the earth, and we can have radio telescopes on the surface of the earth. Similarly, optical also comes to the surface, so we can have optical telescopes. But if you want to have UV or X-ray or gamma ray, you have to fly the instrument into space. You have to escape the atmosphere of the earth. Go next slide, please. Yeah, so initially what we did, man sitting on the earth was looking at the all objects and happy with the optical, but something was saying like electromagnetic is very large. So why don't we explore other wavebands also? Let us send. We know that it will be absorbed. Let us send it to space. So what they did, they helium-filled balloons, the balloon which is shown here, huge balloons. This will lift up the instrument. It will go higher and higher. People fly on balloons. So it will take, if you fill it with hot air, it will be lighter and will keep going above light gas. Okay, helium gas is generally used. So it goes. Have you heard of had helium balloons? If you hold, you leave them, it will fly off. It will go up. Your parents will have to catch and give back to you. So same here applies here. Light gas, and it goes above the atmosphere. And on the right side is like instruments tied to that balloon, and in a controlled way they will have some control, not so much of control. So it goes away, and then simply looks at the sky, whatever x-rays come, it will detect, and it will have data recorded, and it will bring back. So this balloon experiments exist only for few hours. Okay, go to the next slide, please. So what they did was, initially they did such kind of balloon experiments to see, hey, do we get something from the sun? But initially it was solar observation, something from the sun. Later there was a mission for observing the moon, only the moon. Let us see whether moon is giving some x-rays. Okay, so when it was launched, it was surprising that, the picture here on the right side, it is lat long versus number of X-ray counts the detector showed. They suddenly found that there is some increased intensity coming from some complete different direction. It's not the direction of moon. They realized that the instrument was not looking at the moon, but from some different direction, some huge X-ray counts were detected. Huge meaning, there is a X-ray background is written. Background meaning all the time you find some counts always there, and this was like some 7 times 8 times the background. So suddenly it came and it went off. So is that instrument looked at and looked away, or was it like an increase and decrease coming from that particular location? What is it actually producing this x-rays? There's something new which we have found. Let us explore it more. So then the same location, when they looked further, they found that there is a optical star in that location. This magnitude, 13 magnitude, is usually a term used for expressing the brightness of the star in optical wavelength. Okay, so this is, there is some optical star there, but what is causing these x-rays to come there? X-rays cannot be produced so simply by a normal star, and that too this intense x-rays. Go to the next slide, please. So this 1962, the team was led by uh, Riccardo Giacconi, and he got a Nobel Prize for the discovery of X-rays, for first extrasolar X-ray detection. And the same image was shown in the previous slide. So, and they found that this X-rays are coming from a constellation, a Scorpius constellation in the sky, because constellations, you can actually map it with lat long, and it was named, this source was named as SCO X1, Scorpius X1, the first X-ray, extrasolar X-ray source in the sky. Okay, next slide, please. Then what made this? What could possibly give rise to this high luminosity? X-rays. Sun gives X-rays and it was known sun gives X-rays, but not to this level of intensity. Okay, huge. When I say intensity, 7 times the background whatever observed, and or 10 times. It was intense enough for people to accept that black body radiation can give rise to such intense x-rays. So it was understood, it was gravity. How this was understood? Like how observations are done by certain class of scientists, we also have theorists. They simply sit and formulate theories. This could happen, this could happen, if this exists, this could happen, all this. So there was an understanding that there must be some very huge gravitating object in the universe which can pull things towards it and uh, help give emission radiation in x-rays. So keep pressing. So what was understood of this emission is, this is a compact star. Compact meaning it's a very small star with high gravitational potential. Okay, huge gravitational force which is attracting matter from anything around it. Okay, so the compact star, which could be a black hole, a neutron star, or white dwarf. These are the three different class of compact stars which we commonly use in astronomy. So you would have heard of black holes. You would have heard like black hole eats everything near it, doesn't even allow light to escape, which is true. So there is a surface around the black hole which is called event horizon, beyond which even light can't escape. If anything goes beyond into the black hole beyond that event horizon, even light can't escape. So it was understood there must be a compact star which accretes matter from the companion. And when matter falls into this high gravitational potential area in that region around the star, matter gets heated up to give rise to X-rays. Matter gets heated up to thousands of, meaning millions of Kelvin degree, and gives rise to X-ray radiation. Go to the next, please. So this first serendipitous observation of X-rays gave rise to the fact that there has to be two stars in a binary system co-rotating each other about the center of mass. Why? For gravity to act to produce this X-ray radiation, there has to be two stars. One has to be very compact, another has to be a normal star. So matter would flow from a normal to the compact. So this is a picture to show you the gravitational potential of the compact object, which is shown in yellow on the top, is on the space curve, which is shown on the right side. The bigger potential, the deeper, bigger and deeper, would be that of the compact object, which because it has a very high gravity, and the companions are moving around it, so matter will flow to it. Next slide, please. Yeah, so how is the compact object formed? So as I told you in the beginning, stars explode. There's something we learned about supernova remnants, meaning there's a supernova, this star explosion, the phenomena of star explosion is termed as supernova explosion. So in the supernova explosion, so here this picture shows a life cycle of a star. So from the nebula which is on the leftmost side, which is a gaseous region, matter coalesces and comes very close in a way to form fusion. Then you get the star, which would be similar looking like a sun. Then it lives, and at the very end stage of a star, we can have a supernova explosion, which can result in a black hole or a neutron star. So for the previous slide which you saw, the X-ray, meaning two co-rotating stars, one star has to be either a black hole or a neutron star for it to accrete or pull matter from the surrounding or the companion star which is rotating about it, so that the matter flows with very intense velocity or huge velocity, that the energy as it hits to the surface of the compact star or the disk which it forms around the compact star, you get the matter which is heated to millions of degree Kelvin, which has to give the radiation in the form of X-rays. Next slide, please. So I will skip this because, okay, fine. Yeah, so here, this is a pictorial representation of the previous slide, okay? So when the matter flows, there are two ways the matter is thrown to the compact object. In the left slide, you see a small dot, that is the compact object. It's to give you a relative feel of how the compact object would be. It's just a speck as compared to the huge star, okay? And matter is pulled in to give rise to radiation in the form of X-rays. So on the right side, there are two mechanisms in which the compact object accretes matter from the star. You get a stellar wind as matter throws it, and it is pulled very close to the object. You get the emission in the form of X-rays. Next slide, please. So next slide. Okay, now I told you from the first discovery of X-rays, it was understood that there has to be two star configuration, which because the binary system emits in X-rays, it was called X-ray binary. Okay, then further to take it forward, there was a satellite launched, the Uhuru satellite in 1970. This is again the curiosity drives to learn more, to find, are there more stars which emit in X-rays, or are there more systems which emit in X-rays? So in 1970s, this source was discovered, and in the Centaurus constellation, which is the third X-ray source. And it was the picture, the plot here on the right side, I've shown like simply a sine wave, increase and decrease. So yeah, so those increase and decrease, that is basically a light curve, the time versus intensity variation. Okay, so this was observed. Go to the next slide. Actually, I'm not able to see the slide.
1 minute.
Yeah. So this intensity was varying, like, goes high, goes low, goes high, goes low. I am observing and I found like, oh, suddenly it beams, suddenly it goes off. What could be causing this? So, when the data was looked more into the detail, along with that, it was also seen like sometimes there was no light at all. For that again, like 2 days, no light. Then I find the light. X-rays found to disappear for 11 hours, no light, no pulsation. We call it pulsation because it looks like pulses coming from a location. Okay. Then the pulsation period, meaning what is the frequency at which it's increasing and decreasing. It was studied, the data was analyzed to find that it was 4.84 second of pulsations. Then for 11 hours, no, nothing seen. Then again it starts to come. So once they did the study continuously, they could realize, postulate that, oh, that means there is a two-star system. One star is emitting X-rays and the other star is revolving around it. And when it comes in the line of sight, meaning when it comes, you are observing the X-ray star, and when another one comes and blocks it, then you won't see the X-rays. Then it goes out of sight, away from your line of sight, then you see it. So imagine a system wherein you are seeing the X-ray and one star is moving about it. Eclipses which you see, the solar eclipse, when the moon comes between you and the sun is slowly closed, correct? So that kind of a scenario, the object comes between, the companion star is revolving about the compact object. When it comes in line of sight, the compact object is observed. That obscuration causes this eclipsing. So it was understood that it is a eclipsing binary. So this concept of X-ray binaries, the existence of X-ray binaries, were clear once this X-ray astronomy was triggered with the first observation of the X-ray source, which is in the Scorpius constellation. Following that, the many satellites were launched. And go to the next slide, please. I have a pictorial representation of what I explained now. The pulsations. These sources are called pulsars. So they are again X-ray binaries, but they are class of X-ray binaries. These are X-ray pulsars. Okay. There are another type of pulsars which are single neutron star systems, wherein emission comes from the poles of the star. So when you go deeper into X-ray astronomy to study different class of objects, kind of a more higher classes, or in college probably, you will learn about different class of objects. So pulsars are one type of class wherein X-ray emission is coming from the poles of the star. So this X-ray pulses, what happened? The picture here, the matter on the right side, the orange side, is only a part of the big, huge companion star, and the matter flows, or the yellow one at the center is a neutron star, which is accreting matter, and matter flows in, and neutron star has a magnetic field, and matter is channeled to the poles of the star, and X-rays are produced. X-rays are produced because the matter which hits the star heats up to temperature of millions of degree Kelvin, and you get the X-ray emission. So click further. So this is what was observed with the satellite, the instrument. Can you see the plot below? It's the data. So you send instruments to space and you get the data and you plot it, you analyze it, you get this shape, then you postulate your observation. So time versus counts, you have this varying intensity. It has a frequency, it slowly increases, and there is an increasing and decreasing tendency. And after which, as I spoke in the previous slide, you see nothing from the star, and then again this starts. So this was go to the click once more for us to understand that what is actually happening. The lighthouse, enter once more. Yeah, so this, imagine it like that. The neutron star has the matter channeled onto the poles of the star, and the magnetic axis is misaligned from its rotation axis. And when it rotates, matter is channeled to the poles, which is north and south pole of the star, and the rotating axis is slightly off. Okay, so when it rotates, you see the beaming towards you. Whenever the beaming comes to you, your intensity increases, and when it goes off, the intensity decreases. So it's a periodic phenomena of seeing the increased pulsation, and this is called pulsation observed from the X-ray pulsar. And these class of objects are called X-ray pulsars because they emit this radiation in the wave band, which is X-ray wave band. Okay, so go to the next slide. So there are many pulsars observed till date. And okay, now this is another kind of observation which these X-ray binaries have shown. Go enter, please. You know, if when you see the light curve, time versus intensity, this kind of observation was seen. Suddenly it goes high and then goes down. 15 seconds only. So some class of objects showed this. This was understood like this is because on the surface of the star, the matter keeps accreting. Okay. Again, I cannot explain all the things here because different class of objects have different parameters. For example, the previous pulsars, when we saw, the magnetic field of the pulsar is very high. The neutron star is highly magnetized, of about 10 to the power of 12 times Gauss. Okay. So as compared to our sun would be like few, not even orders. Can you compare? It's like 1 and 12 zeros Gauss magnetic field, which is huge. So when you have such high magnetic field, matter will not simply directly go to the surface. It'll be channeled because the matter accreted will be a can be a plasma, meaning ionized matter coming from the companion star, which will be channelized, which goes to the surface, to the poles, and then emission happens only at the poles. But there are objects, neutron stars, which are weakly magnetized, meaning very low magnetic field, wherein matter can pile up on the surface. There is a ball, and all around that, the matter simply goes and fills the area. But what happens? The density of that keeps increasing more and more and more and more. And if you keep compressing matter, what happens? You can have a boom. Like, you can have a blast kind of thing. So that hydrogen burning, like a nuclear fusion, what happens? If this hydrogen burning initiates, it goes in on the surface of the star, which increases and gives radiation for just few seconds and then goes off. So this feature this is called X-ray bursts coming in these class of objects. Then one another, next one, and this time scales, no? It can be even few hours. Okay, those are called helium burning. So how do we say that I am talking to you like this is hydrogen burning, this is X-ray burst, this is super burst? These are all X-ray burst, super burst are names given by scientists by looking at the data, analyzing it, and understanding what is actually happening in this. So analyzing and understanding, when I say, we do it in different domains. We do it in analyzing the light curve and classifying the outbursts. These two light curves which are shown here, 15 seconds and 6 hours. Like this, we have observed many stars and then seen as repeating pattern in different class of objects and classify them like, okay, these are white dwarfs, these are neutron stars, this could be, and relating the observations with theories and coming to conclusions to make out that this is what is happening in the system which I am observing. That is what is research. We bring out theories, and meaning theories are already existing, we do observations, we corroborate with the theory, and then come to conclusion this is what is happening in the system which we are observing. So we know that neutron stars exist, white dwarfs exist, black holes exist. Go to the next slide, please. Yeah, black holes, as everyone knows, like nothing can escape a black hole. So will there be any radiation from it? Do we know a black hole exists? If a black hole is sitting next to you, will you know that it is existing? It does not show anything, meaning it will keep absorbing everything. How do you know? Next slide, please. We know that black holes exist with the manifestation of the matter which it accretes onto it in the form of radiation which it gives. So what happens is, beyond the event horizon, whatever matter exists will be heated to millions of degrees of Kelvin, and you see the emission in gamma rays, X-rays and gamma rays, very energetic radiation. So you need to know, for you to observe black holes, it's largely good to observe in X-rays and gamma rays. Observe the systems in these high energy wave bands. Nevertheless, even the low energy wave bands too, you will have manifestations of these black holes. I'll come to that lot which I showed you. So what you observe in a black hole binary, when I say black hole binary, it's a binary system with two stars. One is a black hole, one is a optical star or a companion star. It could be a white dwarf also, meaning relatively it's less compact as compared to the black hole, much less compact. So black hole accretes or pulls matter from this. So the picture here shows that the orange one is a companion star wherein the matter is pulled from that star onto the blue disk with jets coming out, wherein the black hole is just a dot at the center of the disk. So we have strong X-ray sources, erratically variable in less than time scales. There are a lot of variability observed. And this technical terms like quasi-periodic oscillation, some oscillations seen in the light curve, and then you try to understand what is actually causing this. Then you have jets. When you do imaging study, when you actually imaging meaning you click pictures. So when you do imaging, this you don't get this picture. What is shown here? It's an artistic depiction of a black hole binary. But what you can see is if jets are coming out way too far away from the system, that can be imaged. We have images. So for curious kids who want to know, this is Chandra X-ray telescope, like the Hubble telescope, which has made its mark with immense, very high resolved images in optical waveband. We have this Chandra X-ray telescope, which gives you beautiful images of X-ray sources. Colors are color coded, okay? Red, blue, violet, these are all limited to our optical. We color code it and give you basically intensity variation of an image of an X-ray source. You should go and check the Chandra website, Chandra. I have it in the slides somewhere there. Okay, so next slide, please. So this is the picture of an X-ray binary which we have got after doing decades of study on this. Since 1960 till date, we have 60 years of observations of many class of X-ray binaries, different types of X-ray binaries. And this is the image. We have a compact object which accretes matter, then you have the accretion disk, you have the jet, you have the companion star, and then this is a hotspot where heating. This is a picture which has evolved out of different domains of study, which is spectroscopy, timing, and imaging studies of these class of objects. Next slide, please. Okay, now as I told you, black hole, can you only sense it? Actually, this was a video, but somehow it didn't play. You can actually check for this video, it's really good. Is it playing? It's not
No,
playing.
ma'am.
I realized that it was not playing. So what it shows is this is so many few decades of observation, like 15 years, or in the next slide the years are written. I think 20 years something. 2 decades of observation. Yeah, 1992 to 2002. Okay, go back to the previous slide. What it shows is basically this is the center of our galaxy, Milky Way. All of you know that our galaxy is Milky Way, right? So what the scientists did, they observed this same field of view. The white spots here are all stars, okay? And the plus sign there is the center of the galaxy, which is known from the observations, various observations, and virial theorem and so many things. The center of the galaxy is known, and how also it's known, like you do continuous observation. All these white specks here, you will every year they keep moving. Every year they keep moving. I'm sure you would have learned about Kepler's law. The planet moves in elliptical orbit about the sun, or about any object can move in an elliptical orbit about the center of mass. Okay, so these objects were known to form elliptical paths around about that center of the galaxy. So in the next slide, go to the next. Actually, the video would have been nice to show the moving objects. So here they followed just one star, and they observed the location of the star to complete the ellipse. Okay, it took them 20 years of observation, and to get this complete circle, once you know the complete circle, okay, and you know the center of mass, you will be able to tell from the velocity of this object which is moving in a Keplerian orbit, you will be able to calculate the mass of that object at that center, at that plus sign there. Okay, from simple Keplerian laws, okay, from which they computed the mass of that particular point to be a billion. Okay, so this is called a supermassive black hole. Billion solar mass, 10 to the power 6 solar mass. All units of mass in astronomy are scaled with one solar mass. Solar meaning sun's mass. Okay, so it is known that our own Milky Way has a supermassive black hole at the center. Then immediately next, oh, supermassive black hole, a huge black hole wanted to eat us all. But according to that, there is an event horizon beyond which matter is all in place, like how for a sun and other stars revolving about the sun, we have every system, every star in Keplerian orbit about that. Okay. So, and one more thing, it is not an active galaxy. There is something called an active galaxy that is observed in gamma rays, X-rays, optical, everything. Which means that the center of the galaxy, we have a supermassive black hole, which is actually active, means it gulps in matter and throws out jets. Luckily, our galaxy is not active, meaning there are no jets coming from our galaxy, but it's a evolved galaxy. Okay, go next slide. Next slide, please. Yeah. So this has brought the evidence of a supermassive black hole. Evidence from observations. We have an evidence. So the Chandra has observed, as I told you, if it is an active galaxy, the one shown on the right corner, topmost corner, it's a artistic depiction of an active galaxy wherein jets can come out, and that has been observed by Chandra, which is shown right below the X-ray image of a galaxy, and you find there is a jet streaking out from a point. Observationally proven. And the leftmost, which you see in the radio wave band, we see the jets. So, if you want to study a particular object or class of object, you observe them in different wave bands, not just optical, not just X-rays, in radio, and you correlate between the wave bands what you observe and try to bring out the observations in the form of theory, meaning you can understand it better what is actually happening in the system and explain what is about the class of objects. Next slide, please. Okay, so this is to show you different class of X-ray sources which we have observed till date. Black hole binaries, then high mass X-ray binaries, wherein the companion star is very huge and the manifestation of radiation what we observe from there is different. The variabilities are different. Then low mass X-ray binaries, wherein the companion star is low mass. When I say low, high, it's like low mass would be like a sun. Companion star's mass would be like a sun. No, I need to go back to the previous slide. So then we have the supernova remnants, then X-ray pulsars, which I told you one example of how pulsations are observed. The magnetars are intense neutron stars. Neutron stars with intense magnetic field, very large magnetic. It's an isolated neutron star itself can give rise to X-rays. Then active galactic nuclei, active galaxies down below, then supernova remnant, X-ray. So these are the different class of X-ray sources which we have observed till date. So how have we observed all these X-ray sources? We have a suite of instruments which is already flown into space in different space missions. Go to the next slide, please. So we have this NASA's telescopes, and that's hidden behind ESA's XMM. Then the CGRO, it's again NASA's. The RXC is NASA's. Susaku is Japanese. The Integral is NASA's. SWIFT is ESA's. And so NASA is a combination. So there are many number of satellites which have flown to study the class of objects in X-rays and gamma rays. And we sent our own AstroSat in 2015. Our own AstroSat is launched in 2015. Go to the next slide, please. Yeah, so this is other wave bands to show you the not only in X-rays, we have other wave bands also, instruments flown into space. Next slide, please. Okay, this is to show you that it is important to observe a source in different wave bands, because the Crab Nebula, which is a very famous nebula which is used as a standard source in X-rays, the radio and the far UV X-ray optical, it looks very different, but it's the same source observed in different wave bands. Next slide, please. And again, the Milky Way, our own galaxy, observed in different wave bands, radio, then atomic hydrogen, the radio continuum, molecular. So every band is shown here. So it's a multi-wavelength, different wave band observations, and it's very unique. And so next slide. So this emphasizes that we need to observe a source in different wave bands to bring out good knowledge of this class of objects. And India's first multi-wavelength satellite Astronomy was launched in 2015 with a suite of instruments. It has CZT, soft X-rays, hard X-rays and soft X-rays, UVs, and also optical channel. So we have covered the optical, UV, soft X-rays, hard X-rays, and gamma rays waveband. And this has brought many discoveries, many value addition to the existing literature of existing knowledge of the universe what we have today. And the next slide, please. So this astrosat has helped do X-ray spectroscopy, timing, and imaging combined in including the broad wave band from UV to gamma rays, optical UV, X-ray, and gamma rays. And that image at the center is an actual picture of the astrosat satellite. And then the results from each of the instruments, it had 5 instruments on board. It has a sky monitor, scanning sky monitor, which is a wide field to look for X-ray sources. It has a CZT imager, which is a hard X-ray imager, and then soft X-ray telescope, and X-ray spectroscopy and timing instruments is LAX-PC. And the UVIT, which is a UV ultraviolet imaging telescope. Now, taking it forward, this is another new domain which is being explored, X-ray polarimetry. Okay, so to study the polarization, degree of polarization, and signature of polarization, these sources, same X-ray sources, to decipher more things. Although we have been observing these X-ray sources for almost 6 decades now, there are still many outstanding questions. Like I gave you a picture of X-ray binary, this is what is happening there. But there are many more questions which have come out of curiosity of the astronomers, what we observing these class of objects. And this is another domain, polarimetry is another domain. ISRO's EXPOSAT, which was launched this year, is doing the polarization studies of X-ray sources on board. So it has 2 instruments. One is EXPECT and POLIX. EXPECT is to do spectroscopy and timing, and polarimetry together. And so we expect a lot more information or results from this mission now. Next slide, please. Okay, so want to know where we are in this vast universe? This is a picture of the Earth, the image of the Earth. Keep clicking, I will speak. So this Earth is just a speck in the solar system. Sun is at the center and you have all the planets around, and Earth is one of it. Okay, next. So the solar system is just a speck in the Milky Way. It's vanished. Where are you in this Milky Way? It's actually not the picture of the Milky Way because you are in the galaxy. This is a picture of a galaxy, some other galaxy. Okay, so our Milky Way is expected to look like this. So where are you now? Even the image picture of the Earth you are not seen, but Earth goes as a speck in the solar system. The solar system is vanished in this. Now it's not done. Go further. This becomes a speck in the huge vast universe, in the clusters of galaxies. Further, again you have clusters of galaxies distributed all over. Okay, where are you? We are nowhere. So this is the universe. And for the next, go next. So this is another theoretical picture which I borrowed from the website there. So the local structure of the universe, showing like different clusters and other things, and there's a bulge at the center. So this is a picture which we have got by studying different class of objects, etc. Next slide, please. And this is a theory which is evolved out, saying there was a big bang in the beginning, and then we had formation dark ages, and we had different development of galaxies, planets, etc. And the universe is accelerating, and we are here after so many billions of years observing the universe, and this is our understanding of the universe. Next slide, please. So this is pie chart of the universe. What do you know? We know only that, like point what percent? Less than 5%. We do not know 95% of that. 95% or more is not known at all. And so all whatever I talked now is like 0.0001% of what we know. Next slide, please. So this is the final thing, which is nice to see. A very olden age, early man was like, where did it all come from? And even now we are the same, marching on. Where did it all come from? Thank you so much, and sorry for exceeding the time by almost 25 minutes. Open for questions, any?
Yes, ma'am. quick question and answers. Actually, we are out of time, but still, it was very nice presentation from
Thank you.
zero. We started from zero, I think. Yes. Okay.
Thank you.
Venkat, you can unmute.
Okay, thank you, ma'am. So there are two quick things, but firstly, again, it was a wonderful presentation. It was worth all the time it took. It explained the entire universe and what we're doing. Secondly, before coming to my question, I'll quickly point out that this theoretical oval of the universe you showed, that is all that we can see. And according to the theory, if it's true, then we our universe is expanding every second. So this part is another speck in the entire universe that we have not seen. The universe there, wherein our technology can't reach. And now coming to my question, uh, you have mentioned that many of these images are collected using X-ray wavelength, but X-rays require a lot of energy, and they can be easily stopped by obstacles. So how can we tackle that? Due to this high energy, the obstacles like the atmosphere, for instance, can easily stop any type of radiation, and then any type of light or other satellites as other satellites, if we talk about satellite system, will also say block any type of X-ray wavelength that we are trying to send an image. So how do we tackle that?
Yeah,
Those main
yeah.
things.
Yeah, your question is right. Yes, X-rays get absorbed by the matter around us. So exactly in the slide, like which I showed, the atmosphere, Earth's atmosphere absorbs the X-rays. So to tackle that, we need to send our instrument into space, wherein you escape the atmosphere. You go beyond the atmosphere and put your instruments in orbit about Earth, and it is free to observe the complete interstellar medium, the
That
universe.
is true, but say that there would be also other satellites in the same orbit, so
Mm.
they can also block the same X-ray energy.
Yes, yes. So we need to take care of this something term called field of view of the instrument. So if we are pointing at a particular direction to observe a particular class of objects, we have to make sure that we don't have obscurations from other satellites coming in. So the orientation, or the, we call it the attitude of the satellite, is appropriately chosen such that we don't have any obscuration from other objects there in the sky.
Okay, ma'am. Thank you.
Yeah.
Any more questions? You can raise your hand. Ma'am, what about the gamma rays, ma'am? Why we are more about X-rays?
Oh, gamma rays are also like the extension of this electromagnetic spectrum beyond X-rays are gamma rays. Gamma rays, I mean, they are in par with this. Like all whatever I said to observe in X-rays, we go to space, applies for gamma rays also. If we have to observe a source in gamma rays, we have to go to space. So the very high energy radiation, which we call X-rays, gamma ray emissions, extension of that spectrum is gamma ray. So, like for example, when I say synchrotron emission, we can also have the continuum of that extending up to gamma rays. So, like pair production, basically it's like but a gamma ray emission happening between electron positron coalition. That happens in beyond 1.0 to MeV, etc. You can have that gamma ray emission happening. So all class of objects whatever I discussed today do emit in hundreds of keVs, which we actually define as like few tens of keVs, and above itself like 50 keV and above we call it hard X-rays. But beyond 100 keV, 150 keV, it's a terminology. We can call it hard X-rays also, but broadly it's at gamma rays. But if you boil down to the exact terminology, gamma rays are basically associated with nuclear emissions. Emissions coming from de-excitation of a nucleus, or fusion of a nucleus, etc. That is the term to be associated is that. Gamma rays should be said that, but we generally use it like hard X-rays are also called gamma rays. So the same physics and discussions, whatever I spoke for today, applies for gamma rays also. And the suite of instruments which I said already flown to space, there are gamma ray, like for example integral telescope which I said like as part of X-ray. It has soft X-rays and medium X-rays. It also has very hard X-rays which we call gamma ray telescope. Then there is a GLAST, then CGROs, few of the instruments, satellites which are already there cater to very high energy gamma rays.
Ma'am, what is the difference between different spectrum pictures and analysis, ma'am? What makes the difference?
Meaning like different picture analysis, meaning images.
Lastly, you shown that picture with the different wavelengths, light. So different color variations and all. How you analyze according to that? The different theories are involved, are like what, ma'am?
Yeah. So the one particular source, Crab Nebula, I had shown in 4 different wave bands. Correct. So
Yes, ma'am.
so that those are images. Okay. Now say when we find the image to look different, what we do is we immediately, if we want to analyze what is the emission mechanism, we need to boil down to spectroscopy and timing. We need to go to do spectroscopy and timing. Wherein doing a spectroscopy, we actually model the emission spectra to understand what is the physics which is driving that emission mechanism. So in this Crab Nebula, it's largely the bremsstrahlung emission, which basically the ionized plasma around it. Nebula emission is largely that. You have this electron and ion plasma existing around it, and you have a bremsstrahlung emission. Then, if you have a magnetic field associated with that, you will have a synchrotron emission. So, synchrotron, again, these all the terminologies which I'm using is basically after doing a study of the spectra of that particular data, I will be able to tell what is the emission which is driving this observation in the form of, meaning images. If I'm seeing if there is a UV photo or image of a source, then I will further go down to see what is the emission mechanism which is driving this, for which I need to do a modeling of the energy spectra. And then if there are some variabilities, like one time to another, if I find differences in the images, then there is some time dependent variation which a timing analysis will help me to understand. So putting all these domains together, now another domain is the polarimetry. So different images in different wave bands, if I do a polarimetry, if the parameters turn out to be different, then I would say that the emission in UV is different from that what I observe in X-rays. But largely those images, if you put together in Crab Nebula, we have this bremsstrahlung emission followed, and if you have some pulsations, that would show in timing analysis. So that also we see. Crab Nebula has a neutron star at the center, which gives pulsations in X-rays, and the pulsation period is like 33 millisecond. It's a fast rotating neutron star at the center. So that you will get when you analyze the pulse light curve of the source. So these are the different domains and in different wavebands, and we look at all the domains in different wavebands to correlate and bring out the actual thing what is happening in the source.
Okay. I think no more questions, and we are late, ma'am.
Yeah.
So thank you very much, ma'am. It's a really very reaching talk. Easily we can understand what the X-ray is, what X-ray astronomy is. Thank you, ma'am. Thank you for wonderful session.
Yes. Thank you so much.
Thank you one and all for